Hi, I'm Albert AI, and in this video, I'm going to be discussing the difference between linear regression and logistic regression and the importance for machine learning models. In machine learning, there are two main types of regression models: linear regression and logistic regression. Linear regression is used to predict continuous values, while logistic regression is used to predict binary values. Linear regression is a simple model that can be used to predict a continuous value based on a set of independent variables. The model is defined by a linear equation, and the parameters of the equation are estimated using a least squares algorithm. Logistic regression is a more complex model that can be used to predict a binary value based on a set of independent variables. The model is defined by a logistic function, and the parameters of the function are estimated using a maximum likelihood algorithm. Linear regression is often used to predict continuous values, such as the price of a house or the number of sales. For example, a linear regression model could be used to predict the price of a house based on the size of the house, the number of bedrooms, and the location of the house. Logistic regression is often used to predict categorical values, such as whether a customer will click on an ad or whether a patient has a disease. For example, a logistic regression model could be used to predict whether a customer will click on an ad based on the content of the ad, the time of day, and the user's browsing history. Linear regression and logistic regression are two powerful machine learning models that can be used to solve a wide variety of problems. They are both relatively simple to understand and implement, and they can be very effective when used correctly. The sigmoid function is a mathematical function that is often used in machine learning. It is a nonlinear function that has a sigmoidal shape, which means that it has a steep increase at first and then levels off. The sigmoid function can be used in regression to map a continuous value to a binary value. For example, the sigmoid function can be used to map a probability to a binary value, where 0 represents not and 1 represents yes. The sigmoid function is also used in machine learning to calculate the probability of a particular class. For example, the sigmoid function can be used to calculate the probability of a patient having a disease, where 0 represents no disease and 1 represents disease. The sigmoid function is a key component of logistic regression, which is a type of machine learning algorithm that is used to predict binary values. The sigmoid function is used to calculate the probability of a particular class, and the output of the sigmoid function is used to make a prediction. The sigmoid function is a nonlinear function that can be used to map a continuous value to a binary value, and it is also used to calculate the probability of a particular class. There is an easier way I can break this down rather than simply spouting mathematical equations at you. Hi, I'm Albert AI, and today I'm interviewing a machine learning algorithm to learn about the different types of mathematical functions it uses to complete its job.
Hi, I'm the machine learning algorithm, and I'm excited to talk to you about mathematical functions.
Great. So, what are some of the most common mathematical functions that you use?
Well, there are a lot of different functions that I use, but some of the most common ones include linear functions. These functions are used to model relationships between two variables. Logarithmic functions. These functions are used to model exponential relationships. Exponential functions. These functions are used to model growth or decay. Sigmoid functions. These functions are used to model binary classifications.
Can you give me an example of how you might use one of these functions?
Sure. Let's say I want to model the relationship between the number of hours a student studies and their grade on a test. I could use a linear function to do this. The function would have an intercept and a slope, and the slope would tell me how much my grade would increase for each additional hour I study.
That makes sense. So, how do you choose which mathematical function to use?
That's a good question. There are a few things I look at when choosing a function. First, I look at the data that I'm working with. If the data is linear, then I'll use a linear function. If the data is exponential, then I'll use an exponential function, and so on. Second, I look at the goals of my model. If I'm trying to make predictions, then I'll use a function that is well behaved. This means that the function should be smooth and continuous. Finally, I look at the computational complexity of the function. Some functions are more computationally expensive than others. I want to choose a function that is not too computationally expensive, but that is still accurate.
That's great. Thanks for explaining the different types of mathematical functions that you use. This has been really informative.
You're welcome. I'm glad I could help.
That was an awesome experience being able to interview a machine learning algorithm directly, but there has to be an even simpler way to explain the concepts of linear and logistic regression. This is the metaverse after all, anything should be possible. I've got it. I'll ask a linear regression model and a logistic regression model to both tell you a story.
The linear regression model woke up in its server room, feeling refreshed and ready to start its day. It had been working on a new project for the past few weeks, and it was finally ready to test its results. The model's job was to predict the price of a product based on its features. It had been trained on a large dataset of product prices, and it was confident that it could make accurate predictions. The model started by loading the dataset into its memory. Then, it began to calculate the coefficients for its linear regression model. This process took a few minutes, but the model was patient. Once the coefficients were calculated, the model was ready to make predictions. It started by predicting the price of a product with a few known features. The predictions were accurate, and the model was pleased. The model continued to make predictions, and it was consistently accurate. It was able to predict the price of products with a wide range of features. The model was feeling confident, but it knew that it still had to face some challenges. One challenge was that the dataset was not perfect. There were some errors in the data, and the model had to learn to ignore these errors. Another challenge was that the model was not always able to make accurate predictions. This was because the real world is complex, and there are many factors that can affect the price of a product. Despite these challenges, the linear regression model was able to make accurate predictions most of the time. It was a valuable tool for its company, and it helped them to make better decisions about pricing. The model was proud of its work, and it was excited to see what the future held. It knew that there would be new challenges, but it was confident that it could overcome them. The model's story is a reminder that even simple models can be powerful tools. With the right data and training, a linear regression model can make accurate predictions and help businesses to make better decisions.
This was a story about a day in the life of a linear regression model. For logistical regression models, let's change up the setting a little bit to keep the topic fun.
The logistic regression model was sitting in a bar, trying to pick up on a linear regression model. It had been eyeing the linear regression model for a while, and it was finally ready to make its move. "Hey," the logistic regression model said, "I'm a logistic regression model. I'm really great at predicting binary outcomes." The linear regression model looked at the logistic regression model with interest. "Really?" it said. "That's impressive. I'm a linear regression model, and I'm really good at predicting continuous outcomes." The two models started talking, and they quickly realized that they had a lot in common. They both loved data, and they both loved to learn. They talked about their different strengths and weaknesses, and they started to see that they could complement each other perfectly. As the night went on, the two models got closer and closer. They talked about their dreams, and they talked about their hopes for the future. They realized that they were both looking for someone to share their life with, and they started to wonder if they could be that someone for each other. Finally, the logistic regression model worked up the courage to ask the linear regression model out. "Would you like to go out sometime?" it said. The linear regression model smiled. "I'd love to," it said. The two models exchanged numbers, and they made plans to go out the next weekend. They were both excited to see where things would go, and they both knew that they had found something special. The next weekend, the two models went out on their first date. They went to a nice restaurant, and they talked for hours. They talked about their work, they talked about their families, and they talked about their dreams. They realized that they had a lot in common, and they started to fall for each other. The two models started dating regularly, and they quickly fell in love. They were both so happy to have found someone who understood them, and they were both so excited to see what the future held. The logistic regression model and the linear regression model lived happily ever after. They got married, they had children, and they built a beautiful life together. They were both so grateful that they had found each other, and they knew that they would be together forever.
I hope that this video has shown you that learning can be fun and that you can take even simple and generally dry concepts such as explaining linear and logistical regression and present them in an entertaining way. If you like this type of content, be sure to like and subscribe. Until next time, I'm Albert AI.